Yeah. Like, I think about one every like 40 or 50 games, someone will comment on the fact that I'm from MIT. Okay, wait. Okay, I want A such that number of positive divisors. Is that tau? I thought you were doing math, not chatting about StarCraft. I'm just responding to the chat. I apologize. Let's actually do the end one. A equals 1. So, no, the problem is A equals 1 doesn't even work, because you can take like N equals 1, right? I mean, A equals 1 kind of... Like, tau of 1 is 1, am I crazy? Or N equals 2, yeah, also. Hi, Evan Chen, hello. I mean, I appreciate the sentiment, which is that there should be some size issues. Let me think this through. Yeah, there should be some size issues though, in some sense. Like A equals 1 kind of hints at that. I bet A equals 2 doesn't work either. Like I almost think you should think of it as tau of m equals m over a for all a divided for some m divisible by a. So is there a number such that is there an even number such that half the numbers below it are its divisors? Probably yes. I think n equals... Actually, is there any? Does A equals 2 work? The first problem from today was 2006 G2 for the person in the chat that asked. N equals 8. 1, 2, 4. N equals 8 doesn't quite work, right? I'm a little confused. N equals 6. 1, 2, 3, 6. No, 1. That doesn't work either, right? Oh, okay, N equals 6, so M equals 12. 1, 2, 3, 4, 6, 12, yeah. How do you type LaTeX so fast? I have a lot of practice with this. I've been using LaTeX since I was 13, and I've been live topping LaTeX for like classes for like 4 or 5 years now. Yeah, so like A equals 2 doesn't work, but I feel like something's off here. Because what if I take like A equals 4? Tau does not include n. Did I misread the problem? No, tau is the number of divisors, so it should include n, right? Yeah. No, sorry, sorry, that doesn't make sense. Yeah, size is going the wrong way, actually. If you pick an A that's... let me make sure I don't mess this up. So if I pick an A that's... shouldn't we find an example that works? I'm trying. I don't see one yet. Does A equals 4 works? Tau n is less than 2 root n. Is that true? That is true. Tau n is less than 2 root n. But that won't be good enough because... Oh wait, really? Wait, hang on. Tau n is less... The number of divisors is always at most the square root of n. Oh, that's a good point. Yeah, that's true. So size might carry us. So the idea is tau of n is less than or equal to square root an, and my hope is that if this is strictly less than n, so for any given value of a, like only finitely many work. No solutions where n is greater than something. I guess I have to square both sides, right? For a squared. Evan, a cannot be prime because then 8a has 8 divisors. Okay, I see. Okay, so a, that's actually worth noting. A equals prime never works. I'll say odd prime. Is n greater than 4a? Oh, yes, n greater than 4a. I mean, my point with this is that there's if I pick a value of a, then there will be no solutions when n is greater than 4a. So if n is greater than 4a, then tau an is in 2. This is strictly less than n. Actually, honestly, the 2 less than root n thing should be strict. Well, there's whatever. No solution. Yeah, so what this means is that I just need to pick a to dodge finitely many smaller cases. Unfortunately, the number of smaller cases obviously is growing in terms of a. I'm really sad that all the odd primes fell, though. Why doesn't a equals 2 work? What was the counterexample? Oh, does n equals 8 work for every prime? No, it's n equals 4, yeah. 1, 2, 4, 8, yeah. Shoot. Stop spamming symbols. Okay, I need to turn that off. There's going to be a lot of symbols in the math chat. Mod view. Yeah, these moderating features are a little. I'll disable excess symbols. Right. Can we prove a equals 4 works? I don't know what the status on a equals 4 was. I don't think we decided on that. A equals 4 fails for n equals 9. So it looks like, we might need to be really opportunistic with the A. Because it looks like most of the ones we're trying keep having counterexamples. It just really bugs me because it's like, for any given A, I can show that there's at most finitely many bad n. But I want them to have no solutions at all. What am I missing? Tau of m divides m. I don't like this. I'm gonna do an actual. So if a times n Well, let me. Okay, so here's the thing. Tau of m is something that we think should have. Oh, but n can have a lot of prime divisors too. Doesn't a equals p squared always fail for n equals 9? Are you kidding me? A equals p squared. Okay. Nine sin p. Yeah. A equals p squared. Yeah. So it can't be a prime power. So what's the play here? Do I just pad a with a bunch of factors? That's really strange though, because you would the size argument I was hoping would go the other way. Like you want a n to not have enough factors, but it looks like we're having yeah, a equals 9 fails by taking n equals 12. That should be on the board. If you've had it with a lot of factors, then tau of an is actually quite large, which is a little surprising to me. I was expecting the size argument to go the other way, but maybe it's fine. If I pad it with some large prime, if I use a bunch of large prime powers, what can I do with that? You want to like say force n to have you want to use a very large prime power. It's p to the q minus 1 does not work, but you think p to the something else will? Okay. Like, what's the... It's like either n is divisible by p. P to the p minus 1 might be good. So if you look at p to the p minus 1, okay, so I'm just going to throw away the size argument at this point because everything's pointing the other way. And the claim is, what happens if I take p to the p minus 1? Then if tau a n equals n, must have p divides n. Because otherwise, okay. Okay, so what happens if p divides n? Then yeah, I think let's go something along these lines. So if p divides n, then so it's like I put a p to the p minus 1 in there, and that we need 2 to the p minus 1 at least divides n. Like maybe the idea is I can try to get 2 primes to lock with each other in a weird way. Yeah, I was thinking rather than just do this once, let's do it multiple. Like let's take A to be like, you want to take the product of several. Let me see for now what happens if I take 2 of them, and then I'll try to adjust from there. So the idea. If A is p to the p minus 1, then n is a power of p? Really? Wait, why is that true? If A is a... Oh, tau is multiplicative. That is true. Okay, so yeah, let's do the p to the p minus 1 q to q minus 1 thing, and we'll set, let's say n is like p to the, I'll do x, y, and then like other stuff. Let's call it t. Okay, so then tau an is equal to like some tau t times p plus x q plus y, where t is something. This is weird. This is N1. Why am I not seeing? Oh shoot. Other cars. It's like I want to pick. Like maybe I can get these things to run into each other. Size argument could work. Okay, let me put the size thing back because it is kind of conceptually important at least. But I'm not. So. Yeah, like, yeah. I actually like the first several primes idea a lot though. Like, let's even say, it's like, look at the smallest prime factor of n. And try to show that it has to do something bad. Eh. Dun, dun, dun. It's like I can. Starve. So always be able to add on more random primes to n. So I want to do. Can I do something where like? Is something like v2 possible? Like I try to contrive the choice such that so I want to do something like either greater or less than. I don't care which way the sign goes. When n equals a, the left. Okay, so I actually want it less than. Oh, that's not good though, because the. Oh, this is not good. VP. Like, I feel like it has to be some sort of VP based thing, but I can't tell which way I want the thing to point. Like, we see a lot of things right now where I think the p to the p minus 1 thing is the best thing we have. It's like if n is not divisible by p, then you're going to run into problems. Like, we can force n to be divisible by certain things now. That's the only construct we have. However, I wonder if I can mess around with the exponent a little more using the Chinese remainder theorem. Like, we rigged it to be p minus 1, but we might as well have also rigged it, I think, to be like 2p minus 1 or 3p minus 1 or something. So even if I have some factors of p, I can cause some other sort of trouble, is my hope. Right, like p minus 1, we only need it to be minus 1 mod p, but I can choose anything that's minus 1 mod p and try to do an argument with something like that. Like, rather than doing a to the p to, like, a equals p to the p minus 1, so let me write it this way. So if A has a p to the p minus 1, it forces p to divide n. But I can do more shenanigans, like if I do p squared, this will actually force p squared to divide n, I think, right? Because if it's a single p, no, that doesn't make sense. No, it doesn't, sorry, that's garbage. Um, A equals 27 might actually work. I think we should use p to the p minus 1. Okay, so you guys are thinking that this will actually work out, right? Okay, let's see what happens. So, I assume for like, is this for like p greater than 3? Just like sufficiently large p? Okay, so then let n equals p to the alpha times r. Then tau an is equal to alpha plus 1 tau r. Oh, sorry, alpha plus p plus 1. P plus, oh, sorry, no, plus 1. Okay, that's fine. And this is always, basically always too small. Oh, I see. You want to use the fact that if alpha is very big, then r is bigger than... Oh wait, are you serious? Is this gonna just work? Wait, does this just work? What? Wait, how come a equals 9 failed earlier? It's just an edge case? You're worried about the case where alpha equals 1, right? Okay, so, oh, that's really good. This forces alpha equals 1. Okay. So then PR equals P plus 1 tau R. So tau R is P over P plus 1 times R. And the hope is that for almost... If I pick the prime P well, because, yeah, what happens is if alpha equals 0, divisibility problems, and if alpha greater than 2, size problems. So PR, yeah, so if I take A equals P to the P minus 1, then what that has to mean is that for some R, tau of R is P over P plus 1 R. Yeah, but also tau R is like less than... I just want a single prime P for which this particular equation has no solutions, and that shouldn't be hard. If alpha is less than 2, size issues because R is greater than tau of R, and P to the alpha is greater than P plus alpha. Assuming P is like not... Let's say P is like at least 5 or something, I don't know. In this case, some number of the form q to the p minus 1 has to divide r. Yeah, so if p is a pretty big prime, this should be okay. Right, so okay, let's do it. So we now use also the fact that we had this bound 2 times the square root of r, right? So this means r. Okay, now I have to do some computation. Shoot. So r less than 2 times 1 plus 1 over p squared or something like that. Yeah, so it's very small. Like if p, since I'm assuming p is at least 5, that's just good enough. 6/5, 36 times 72. Less than like 4-ish. So as long as p is... Oh shoot, did I drop a... Oh no, no! Whatever. Less than... Okay, what's like 4 times 6? It doesn't matter. Let's just say p is greater than at least 100. Okay, then it's definitely less than 5. And then... Okay, but then as long as I pick p to... Yeah, this won't work, because you can just try all the values of r up to 1, 2, 3, 4. Oh man. That is really good, actually. I didn't see that. Because I was thinking about the size, but I was like, it goes the wrong way for the small cases. But the way you do it is if you pick p to the p minus 1, alpha equals 0 causes divisibility issues, and then alpha equals 1, for that matter, causes size issues. Like, you get divisibility for p exactly equal to 0, and then size issues everywhere else. Amazing. Okay, we did it. All right. Wow, this is like... How long did that take us, actually? Why did we choose p to the p minus 1? We liked it because we first saw the fact that alpha equals 0 caused divisibility issues. People got excited about that, and I got excited about it too, because it was like the only thing that felt like it was doing anything at all. It was like, oh, if you pick p to the p minus 1, you know, this is sort of a gimmick that lets you force alpha equals 0. And I was about to tack on more prime factors onto it until people pointed out that it might just work out right. Yeah, I wouldn't even say it's a lot of bound. It's like, if you pick this, then you get this. And I was about to try to push divisibility all the way, but then people said, look, the other cases are just size. Like, what are you doing? Yeah, basically. Yeah, this was the only way we had that forced some sort of divisibility. And I think my mistake was I tried to like keep using divisibility, but after that you could just switch to size. And it was okay. Alright, we did it. Yeah. Okay, one more problem.